Well, hello everybody, and welcome to the slightly surreal experience that is We Brew with you live in my living room. I have to say, over the last few days, I've gained a newfound respect for YouTubers because this definitely isn't as easy as I thought it would be, and it's definitely a new one for me. Definitely a learning process. So this is going to be the first of hopefully several We Brew With You online videos. Today's going to be about lager production, but please, if you have any recommendations or anything that you would like us to talk about, please send us a message and let us know. So the aims for today's session are to discuss lager and the history of industrial lager production. And we're also going to look at the genetics of the lager yeast strain and how it came to be. And then finally, we're going to look at several techniques for achieving the lagering process and what the lagering process itself means. So without further ado, I'm going to begin. So industrial lager brewing is actually a relatively recent phenomenon. It's not been around for that long. Lager itself has been brewed since the 1500s, but this was in rural Bavaria, and it would have been limited to the times of year where it was cold, so outside of the summer months. In addition, these beers would have been dark, not light. So not really a process that was suited to industrialization. And between now and the early 1500s, this beer has become the most popular beer style in the world. So how did this occur? And to my mind, there are three distinct innovations which drove the popularity of lager beer. Now, they say a picture equals 1,000 words, and I'm lucky in that I have many, many pictures for you today. So I've borrowed a little gadget from my wife, who's a teacher, and this allows me to show you pictures. So as we go through the process, I'm going to get this camera and show you some diagrams. So the first diagram is going to illustrate developments in malting technology. Look at this, isn't it great? So prior to the 1700s, malt would have been germinated as normal and steeped as normal, but then it would have been dried, and it would have been dried directly using wood fires or coal fires. Now, wood fires and coal fires, as I'm sure you're well aware, produce a lot of smoke, a lot of color, and probably quite a lot of flavor as well. So when you were doing this, you would end up with a dark malt that was quite smoky, quite acrid, and it would produce very, very dark beers. So this was it was done originally, so ancient times. Then, as we went into the 1700s, people started to dry the malt with coke or charcoal. Now, this is it's a modified form of coal or wood, and it burns at a very high temperature, but it burns very very cleanly because it's a very pure source of carbon. So you get very little color pickup doing it this way, and you get much lighter malts. Some British maltsters were actually doing this well into the 1900s, but what you do find is it produces carcinogenic nitrosamines. So it's generally not done anymore. These days we can produce very light lager malts, and we do this by indirect heating with hot air. So we'll uh, heat some air using gas, usually gas, doesn't have to be gas, and then this will pass through some pipes as an exhaust, and over these pipes we will blow some hot air from a fan, and that will dry the malt. So it's very easy in this way to produce very, very light malts compared with very, very long time ago when they produced dark and smoky malts. Now, interestingly, there was a brewer at a Pilsner Urquell by the name of Joseph Groll, and he was the guy that developed the first pale lager malt using this method. And this brewery claims to have produced the first ever pale lager, and it's still brewing to this day. So the next picture and the next development I have for you is this guy. Now, what I've learned in my research for this talk is that nobody smiles in old pictures ever. I mean, even like people that work in beer, they never smile. This guy is Carl von Lind, and he developed the ammonia refrigeration system. So he allowed breweries to be able to chill their beer all year round. So they'd gone from being able to brew only in the wintertime to being able to brew at all times of year. And he sold these to breweries. Next innovation and a next grumpy looking person. This is Louis Pasteur, and he was a guy who did quite a lot of different things in the world of microbiology. Specifically, he produced the first rabies and anthrax vaccines using some slightly dubious methods. He used to test them on live people and did all sorts of things that were a little bit morally dubious. He also had the pasteurization process named after him. But what he's best known for in the brewing world is the discovery that yeast is responsible for alcoholic fermentation. So prior to this, it was thought that yeast cells, which had been observed at this point in beer, spontaneously broke down and produced alcohol and carbon dioxide in the process. Now, he proved that actually the yeast cells were the causative agent of fermentation, so they were the reason that alcohol and CO2 was being produced at all. So that is Louis Pasteur. So next we have this guy. Next famous brewing microbiologist is Emil Christian Hansen, and he isolated a pure strain of yeast from a multi-strain bottom fermenting culture at the Carlsberg brewery. Now this strain had been brought to the brewery some 4 decades prior from the Spaten brewery in Munich, and it was composed of 2 strains. So it was a multi-strain culture. Now the brewery were having problems with thick fermentations. They were too bitter and they took too long, and it was proving really problematic for the brewery. They were struggling with sales, and this guy, Christian Hansen, managed to isolate the 2 different strains and prove that one of the strains was predominating in the mixed culture, and this was the cause of the fermentation problems. Now, he named those strains. The first strain was the wild yeast, or the Carlsberg 2 strain, which was the one that was causing the fermentation problems, and this was actually found in a orchard nearby, indicating that it had probably originated there, and it was a wild yeast contamination. The second strain, which he named Carlsberg 1, became the Carlsberg yeast strain, so the lager yeast, as we now know as Saccharomyces pastorianus, although it was originally classified as Saccharomyces carlsbergensis. Now, Emil Christian was a really nice guy. He was a good bloke, and rather than keeping this innovation or this pure strain to himself, he spread it around the world. So he would send it all over Europe and all over the globe. Which is one of the reasons why the strain, or the lager yeast strain, is so prevalent in the world today, because he was a nice person. I'm going to talk a little bit about the genetic origin of lager yeast. So it's only recently been deduced where lager yeast came from. Now, normal fermentations, or ale fermentations, are fermented with Saccharomyces cerevisiae. It's a strain that we all know very, very well. And it's long been known that the lager yeast was a hybrid of Saccharomyces cerevisiae and another strain, but nobody knew what this strain was until very recently. In fact, not until 2011 was this strain discovered. And the strain was Saccharomyces eubayanus, which is this strain here. And it was discovered living in the forests of Patagonia in Argentina, and it was discovered to have a similarity to the lager yeast genome. So it had a 95% similarity to the half of the genome in the hybrid strain that was from Saccharomyces eubayanus. Now, this strain is quite interesting. It's cold tolerant, so it can ferment at cold temperatures. It's POF positive. This is the phenolic off flavor that you get in Belgian beers, but you don't really get them in lager beers, which is interesting. It's also maltodextrinase negative. So this means that it won't ferment the 3-glucose sugar within a brewery wort, which isn't very useful if you're trying to make a fully attenuated beer, and is not normally a characteristic of most lagers. So we now know that the parents of the lager yeast strain, the Pastorianus, are Saccharomyces eubayanus and Saccharomyces cerevisiae. What we don't know is how that lager yeast hybridization event happened, where it happened, and how it then became to be used in 15th century Bavaria. That is still very much a mystery. Now, since the Saccharomyces eubayanus was discovered in Argentina, it's also been discovered in Wisconsin and in Tibet, and it's often associated with trees, quite often oak trees as well. So it's thought that perhaps the strain traveled to Europe in a barrel, and that's how it got into European brewing fermentations. But interestingly, that strain has still never been found growing in Europe, so it's still a bit of a mystery. So we're going to move on a bit here and talk about a bit of genetics. So chromosomes are sites within cells where DNA is stored, and on these parts of DNA, there are genes, and these genes encode proteins. Now, organisms have different numbers of chromosomes, so different copy numbers of chromosomes. You or I, a human, we are diploid, so diploid here, and we have 23 pairs of chromosomes, or 46 in total. Now, brewing yeasts tend to be either triploid or tetraploid, and they have 16 chromosomes in total. Now, when the hybridization event between Saccharomyces cerevisiae and Saccharomyces pasteurianus took place, some of the genes from the parents were mixed together to produce two separate types of lager yeast. It's thought that this happened on two separate occasions, so there's actually been two separate hybridization events in the history of lager yeast. Now, this has created two different types of lager yeast, two strains. One is called type 1, or the Carlsberg strain, and one is called type 2, or the Fryeburg strain. Now, interestingly, in type 1, you see it's a triploid strain, so it's got three sets of chromosomes. Now, one set of those chromosomes comes from Saccharomyces cerevisiae, this one here, and two sets of those chromosomes come from Saccharomyces bioanus, this one here. So it's a triploid strain, three sets of chromosomes, but it's more Saccharomyces eubayanus than it is Saccharomyces cerevisiae, if that makes sense. Now, the type 2 strains, or the Fryeburg strains, are tetraploids. So this means it has four sets of chromosomes. And it has two sets of chromosomes from eubayanus and two sets of chromosomes from Saccharomyces cerevisiae. So it's actually almost equal on the two types. Now, when you get a hybridization event like this, you get a phenomenon known as transgression. And that is when the advantageous traits within the chromosomes tend to predominate. So I have here a table detailing how the different lager yeasts behave in fermentation. So the Fryeburg strains, which is more Saccharomyces cerevisiae, so almost half Saccharomyces cerevisiae, are more sensitive to low temperature, i.e. they don't like to ferment at very, very cold temperatures. They produce more higher alcohols than the type 1 strains, more esters, but they utilize maltotriose. They ferment more of the extract that's available. They also have a much greater fermentation performance. They can go a lot faster and they can consume the sugar a lot quicker. Now, the Carlsberg strain, which is more eubayanus, is less sensitive to low temperature, so it's quite happy at low temperatures and it doesn't really mind. It also produces less higher alcohols and less esters, but some of the strains don't utilize maltotriose, which isn't a very useful characteristic of a brewing yeast strain. It's also nowhere near as good at fermentation, and it's probably because of this that actually the Carlsberg strain has almost died out in industrial brewing. Most industrial breweries use the Fryeburg strain, which is more sensitive to low temperature, but has a much higher fermentation performance. So we've looked now at some of the history of lager and how it became industrialized. We've also looked at some of the genetics of brewing yeast and where it came from. And I want to look a little bit at the lager process itself, because it's an interesting process and it has some distinct aims. So the aims of the lagering process, this is just a bullet point, so forgive me for just reading out. But reduction of residual extracts, that's reducing the amount of sugar that's remaining in fermentation and creating more alcohol. Scrubbing of unwanted volatiles, so that would be mostly hydrogen sulfides, that rotten egg smell that you quite often get in and around lager breweries. You want to get rid of that. Obtaining the correct level of dissolved carbon dioxide. Now that's just the fizziness of your beer, so you want to have enough extract there that you can create fizzy beer. Reduction of acetaldehyde. Now, if you've heard of green beer, this is the green apples flavor you get in young beers. Now, the lagering process will eventually clear that up. Reduction of VDKs, that's diacetyl, so you're talking rancid butter. It's a flavor that most people really don't like in their lagers. Some lagers are famous for having a diacetyl taint to them. I actually don't mind it. Personally, I don't mind it as a flavor. Reduction in yeast cell concentration. So if you're going to be going on from your lagering process and you need to be filtering and you want to have nice bright beer, you need to reduce that cell concentration. And some lager yeasts tend to be quite unflocculent, so they don't like to drop to the bottom of the fermenter. So a long lagering process can help to reduce this cell concentration. Finally, an increase in clarity. So if you're trying to produce filtered beer, you really want to be hitting that filter with the least dissolved solids possible, and a long lagering process will help to do this. Now, these days, very, very long lagering processes are not desirable because economically it doesn't make a lot of sense. You've got lots of expensive equipment and you're not utilizing it. So if we can achieve all of these things in a faster time, it makes economic sense to do so. If you can achieve all these aims, really there is nothing more to be gained from leaving your beer in the tank for an extended period of time. So what I want to explore now is 3 different methods for the lagering process and the pros and cons of each. Just before we go through that, I just wanted to go through diacetyl reduction. So diacetyl is a chemical that's naturally produced by yeast during the fermentation process, and it's formed from a flavorless precursor, which is the alpha-acetolactate, which is this chemical here. Now, this chemical is excreted from the yeast cell, and it is non-enzymatically reduced into diacetyl. So this process here, this happens without any yeast involvement at all. Now, that's important because during fermentation, the ability of the yeast to mop up diacetyl is about 10 times its ability to create it. So during fermentation, you don't get a great deal of diacetyl buildup. It's towards the end of fermentation, when your fermentation slows down and the yeast becomes less active, that the diacetyl will start to spike. Now, given enough time, healthy enough yeast, and a warm enough temperature, the diacetyl will be taken back up into the cell, and it will be reduced into acetone and then into flavorless 2,3-butanediol, which is this chemical here. This is probably one of the main aims of the lagering processes, and it's one of the ways that you can keep track of how successful your lagering process is. Once the butanediol has dropped, once the diacetyl has dropped, it's likely that most of the other undesirable volatiles will have dropped as well. Now, some breweries that don't necessarily have the time to do long extended conditionings and diacetyl rests can actually cheat. So there's an enzyme called ALDC, which is this one here. And what that does is it enzymatically reduces alpha-acetolactate into acetone, and it bypasses the diacetyl step altogether. So it just speeds up your diacetyl reduction process. So now moving on to look at some of the different ways of lagering. Sorry, that's upside down. This would be your traditional lagering process. So your beer is going to be fermented until all but 2 to 4% of the fermentable extract is remaining. At this point, you would pump it into a secondary vessel, ensuring that there's enough yeast in it for a secondary fermentation. And during this time, the temperature will be lowered from 10 degrees to about 1 degree to 3 degrees over 2 weeks to 3 months. So it's actually a very, very long process, the traditional lagering process. So to start with, once you've transferred it to your secondary fermentation vessel, you will let a lot of the CO2 bubble through. So you will let it come off the top of the vessel, and with it, it will take some of the unwanted volatiles, particularly the hydrogen sulfide. The vessel will then be allowed to pressurize, so you will seal it up, which will carbonate the vessel, and then it's left for a very long time. And during this time, the insoluble protein and tannin and the yeast will drop to the bottom. So that's your traditional lagering process. I have here a graph that details it. So the black dashed line here is the gravity. So the gravity of the fermentation, you can see it dropping over the time period. The blue is the temperature profile. So we're talking about a traditional lagering process. You're talking about 7 to 8 degrees of initial fermentation temperature, maybe rising up to 10, and then dropping that just before you transfer to the secondary vessel here. Now the orange line here, this one here, this is the diacetyl level. So what you can see here is that the diacetyl level takes a very long time to drop below the red dashed line, this one here, which is the flavor threshold of diacetyl, which is about 100 parts per billion. So this is a traditional process, and you can see at a minimum it's taking 20 days. And if you include time to drop stuff out of the beer, it's going to take a much longer time than that. So whilst it's a very fun process and it's very interesting, and a lot of people do still do it, If you're doing intensive lager production, it's probably not for you. And there are some ways of speeding up the process. I'm going to go through one of these next. So this would be traditional lagering with a Krausen addition on transfer to the secondary fermentation vessel. So in this process, the fermentation time is quite similar to the traditional lagering process. But once you've exhausted the fermentable extract in the primary fermentation, you will transfer it into a secondary fermenter, and at the same time you will add a portion, probably 5 to 10% by volume, of fermenting beer from another fermentation. Now this addition of fermenting beer comes with it a large cell concentration and additional extract. And what that does, and I'll show you on the next chart, is that it allows your diacetyl to come down a lot faster. This is because we've added that fermenting yeast into the process. So do you remember I told you that during fermentation, the ability of a yeast to reduce diacetyl is 10 times its ability to produce it. In this diagram here, you've got your diacetyl spiking, and as you transfer to the secondary fermentation vessel here, you add your Krausen, and then the diacetyl level starts to drop right down. So doing this, you can actually get to within diacetyl spec within about 10 to 12 days. Following that, you still have your process where you're reducing down the dissolved solids and the yeast as well. But this can be sped up in various ways using centrifuges or using finings as well. Now, finally, my third technique for reducing diacetyl in a lager fermentation would be warm conditioning. So in this process, you're allowing primary fermentation to proceed, but instead of keeping it very cold, like in a traditional lager fermentation, you allow it to rise. So from say 7 or 8 degrees as a starting fermentation temperature, you will allow that fermentation to rise up to about 13 or 14 degrees. Once it's at 13 or 14 degrees, you will then take yeast off the bottom of the tank to stop any autolysis, and you will allow that yeast to bring down the diacetyl level, which will take place much more quickly because it's at a warmer temperature. You can then centrifuge the beer to reduce the yeast content and send it to a secondary vessel where you can either clarify it over a long period of time, or as I said before, you can use some finings additions, and you can use artificial carbonation or natural carbonation by using some additional sugar. Now this is the graph of the fermentation using warm conditioning, and you can see that it's much quicker, right? So your gravity comes down much quicker, and that's because the temperature is a lot higher. But at the same time, your diacetyl level drops much quicker as well. And this is just because the yeast is more active at this temperature. Now, there is potentially a downside to this. When you're fermenting lagers at warm temperatures, you're creating a lot more volatiles, so esters and higher alcohols. So this is going to give you a flavor profile that especially if you're trying to move from a traditional lager process into a quicker one like this, might give you more of a flavor profile than you necessarily wanted from your beer. So it might be more fruity, it might be more alcoholic, and actually what you want is a more neutral product. So in order to combat this, one of the things that you can do is to ferment warm, but then add some pressure to the fermentation as well. So maybe 50% through the process, you will bung the tank, so you'll seal it up, and you will allow the pressure to rise. Now what this does is it's going to increase the level of dissolved CO2 within your beer, and this will actually protect against ester and higher alcohol production. Now the reason for this is because a lot of the reactions that take place which produce these chemicals are decarboxylation reactions, and if you have a very high level of carbon dioxide within the wort, it will actually inhibit these reactions. So if you want to create a beer and you want to do it quickly, you can add a bit of pressure, and that will actually help quite a lot. Now, this is the only method of the three that I've actually tried in person. Now, I used to work in a brewery called Darkstar in the southeast, and we produced a lager, but we didn't have the luxury of long tank times. So we used to ferment like this, and I think it used to take us about 8 days. We then used to do a 4-day diacetyl rest at 15 degrees whilst yeasting off. And then we would crash cool and chill for about 4 days at -1, and then filter it. So our whole process could be between 15 and 20 days, depending on how much of a hurry we were in. So it can be done. Now that's me done talking about lager for the time being. I hope you've learned something today. I mean, the idea was to go over some of the history, so I think you've got a little bit of the history of that. I think you've got some of the genetic history of the strain as well. And we've gone through three different techniques for fermenting and lagering. Now, I'd like to open up the event to questions and answers. So if you'd like to do that, I'd be more than happy to answer any questions you've got. So that's me back again. Thank you for listening. Any questions from anybody? Hello. Nice to see at least my colleagues are watching. Ah, I can see it. Sorry, I hadn't scrolled down. I can actually see them now. Andy, are some lager strains more susceptible to VDK production than others? Yes, absolutely they are. Pilsner Urquell, I think, is one that I spoke about before. This is well known to have high levels of diacetyl, and I think it's acceptable within the style. So yes, some strains will produce more than others. What yeast count would I expect before transferring to secondary? Probably between 1.5 to 2 million cells per mil would be ideal. That should give you enough for a secondary fermentation. What is my personal favourite style of lager? Ooh, that's a tough one. Probably like a darker Munich lager. Certainly not Carling. What can I tell you about Kolsch yeast? So Kolsch yeast is an ale strain, which tends to ferment at cooler temperatures. So it's a beer that undergoes a process much like lagering. So it's lagered, but it's an ale fermentation. But genetically, it is a ale yeast. Any advice for anybody using cylindrical conical tanks? Yes, absolutely. I mean, you can do all of these things in cylindrical conical tanks quite easily. If I were you, I'd probably go for the warm conditioning one, just because it's a bit quicker and a bit easier. So you can allow your fermentation to rise in temperature, cap it so you can get your CO2 build up and your pressure, and de-yeast at the same time. But then you can also chill it down very, very easily in the same tank. So it can work as a single tank process, especially if you're not filtering or anything like that. Do you need to oxygenate the wort with dried yeast? No, you don't. The way we produce our yeasts means that you don't need to oxygenate the wort when you're using dried yeasts. Some do, and it can give it a kick, particularly if you're doing very, very strong worts or very alcoholic fermentations. It can be advantageous, but you don't need to, no. Can I expand a little bit on the use of ALDC? Yes, absolutely. I can go back to the graph if I can find it. Sorry, these are just my own personal notes here. So ALDC, that's this enzyme here. And when the yeast produces alpha-acetolactate, which is this precursor molecule here to diacetyl, the ALDC will take this precursor molecule and it will enzymatically reduce it to acetoin. So it will go over here. And in doing so, it will skip out the diacetyl production step. So you'll get this step written off. I mean, in practice, you will actually get some diacetyl production at the same time, but this will vastly speed up the reduction of your step from alpha-acetolactate into the flavorless butanediol. Well, I can barely keep up with the questions. Simon, How would you produce a Helles rather than a Pilsner? Is it just the malt hop bill, or is it the water, or is it the fermentation as well? Um, to be honest with you, I think the majority of the differences lie within the raw ingredients, so the malt bill and the hops. Yes, I don't think you would need to change the fermentation too much. Would you recommend dumping cold break from the fermentation before the yeast pitch? Uh, I have tried it in the past, and what we found was that we didn't see a great deal of difference. I don't think there's any downside from removing extra solids from the fermenter, so I wouldn't necessarily discourage you from doing it. But if it becomes a problem and you have a lot of wastage, then maybe it's best to be avoided. What is the best pitching rate for a Pilsner beer? That really depends on how strong it is or how cold it is. So I would vary the pitching rate on the basis of wort strength and fermentation temperature. So if you're going for a very strong wort and you're going at quite a cold temperature, I would up it quite considerably. Thanks for your stream. Beyond the VDK reduction, what was the extent of yeast activity during lagering? So it's not that active. It's reducing volatiles and it's producing CO2 very, very slowly, but it is a very, very slow process. The yeast isn't very active during the lagering process, and that's predominantly just because it's so cold. No yeast is really, really happy at very, very cold temperatures. Can open fermentation produce a cleaner lager in a shorter time? Um, that's interesting. By open fermentation, do you mean not pressurized fermentation? I'll answer anyway. You can comment if you get the chance. Um, Probably not, to be honest. So one of the things that wheat beer brewers is that they do is they actually ferment in open top tanks, and that's to increase the levels of volatiles within fermentation. As I mentioned during the stream, if you pressurize your fermenter, you actually produce a slightly cleaner fermentation because you get less decarboxylation reactions happening and less ester production. So an open fermentation wouldn't necessarily produce a cleaner lager. That's not to say it couldn't produce a perfectly reasonable and very nice lager, though. I would still give it a go. So I'm waiting on some questions. I'll give it a few more minutes. So, what makes German lager so good? I was having a discussion with some colleagues the other day as to what makes German lager so good. And if I'm honest, I think it's attention to detail. I think the process is just really, really well controlled, and everything is looked at a very, very large amount of detail. I mean, industrial lager brewing in the UK, it's probably quite different to a traditional lager fermentation in Germany. I mean, we could probably do a turnaround in 2 weeks and at quite high temperatures. So, maybe that has an effect. I think it's quite likely, but I think it's attention to detail across all fronts. I was chatting, and I think particularly on glassware and head retention, if it looks great, you expect it to taste great. And I think that's something that the Germans do really, really well. Why is dried lager yeast more expensive than ale strains? It's a good question. Lager yeast is hard to grow, so it yields a lot lower than an ale strain, and hence the difference in price. Does step mashing contribute to overall lager quality even with well-modified malts? Possibly. You activate a lot of different enzymes in the decoction mashing process, so it could. The decoction mashing process, for people that don't know, is when you remove a portion of the mash and you boil it and then you mix it back in again with the rest of the mash. And in doing so, you allow stepped rises in temperature. So in German brewing, it's traditional to start at a lower temperature and then perhaps do two decoctions. So you take two portions of the mash out, you boil them, and you add them back into the main mash vessel. And the steps tend to be protein rest, so you break down protein, which possibly has an impact on head retention, but may just be making up for the fact that you've got a higher protein and less well modified malt. And then you have your saccharification step, which is when you get most of the starch breakdown into sugar. Now, interestingly, the Czechs, so Pilsner Urquell, they actually do a triple decoction mashing process, and they claim that this has a very large impact on the quality of the lager. Whether it does or it doesn't, I wouldn't like to say. One thing which is probably true is that it actually increases the colour because you've got more Maillard reactions going on. So Pilsner Urquell is a darker lager, possibly because of the triple decoction method. Sulfur from matches. Okay, so yeah, there's different types of sulfur. So what you're referring to there is not the rotten egg smell. This is like matches is sulfur dioxide, and this is produced naturally by yeast during fermentation. It's actually an antioxidant, so a little of it is quite good. A lot of it is not quite so good. Um, it's actually not very easy to reduce if you've got a struck match flavor in your beer. Hydrogen sulfide, which is the rotten egg, is very volatile, so it'll come off very easily, whereas struck match is not so easy. So it probably won't reduce down quite as much as you would like. Oh, Brian's here. Hi, Brian. So I'm going to wait a couple more minutes, try and get a few more questions in if there is any. Good morning. That's not a question. Do lagers require longer boils? That's really depends what you're trying to achieve with your boil. So lagers, some of them tend to have a higher DMS content, and DMS is reduced during your kettle boil. So if you're actually wanting to produce more DMS in your lager, then maybe you would go with a shorter boil. But it depends what you're trying to achieve with your boil, really. I don't think there's any reason why they would necessarily need a longer boil, unless you were trying to achieve something different to your ale boil. Tips on improving head retention. If you can get some more foam forming proteins within your beer, that would be a good way of improving head retention. So maybe a bit of a wheat addition might help. So that's a possibility. It really depends on what's causing your lack of head retention as well, because it's perfectly possible to have enough protein in your beer to have a good level of head retention and still have issues with it. So it could be something else. So I probably need to look at the process in a little more depth. Is it a good idea to use saved trub as priming yeast? Uh, by priming yeast, I assume you mean yeast to cause a secondary fermentation. Uh, Probably not. I mean, what you really want from a priming yeast or a secondary conditioning yeast is the highest possible level of yeast health, so that you can get the fastest and most healthy secondary fermentation. So if it's already been through a fermentation process, it's probably exhausted and not in the best of nick. So I'd suggest probably not. What is the highest alcohol tolerance for lager yeast? I think that would depend very much on the subspecies of lager yeast that you were using. Some will be higher than others, but I would think it'd be in the range of 13. I could be wrong though. I'd need to look that up. Is it true that 3 months for lagering is the sweet spot and that longer is useless? Um, my personal opinion is if it's longer than 3 months, yeah, I think so. I mean, if you haven't achieved what you're looking to achieve in 3 months, I think you need to start looking further upstream and see how you can impact the process there. Because waiting for longer than 3 months is it's not very practical. Yeah, the struct match. So send me an email on that one. I'll share my email address later. But I'd imagine if you're getting a lot of struck match flavor, it's probably to do with yeast health. So it's probably yeast that's not very happy. So it could be that you need to alter your pitching process or the way you store your yeast. Can I request a sour beer production seminar? Yes, absolutely. I think our colleague in Catalonia actually did one a few days ago. So I'm quite happy to do a sour beer seminar at some point. Anything in particular you'd like us to go over? We can talk about kettle sours, we can talk about traditional souring, you name it. How can you ferment a lager without compromising cycle time? How cold can you ferment a lager without compromising cycle time? You mean how cold can you go without it being too slow? Ooh, that's a pretty tough one, Alberto. Um, I think you'd probably have to experiment, but to be honest with you, I think if you want it to be, like a reasonable speed, you probably want to aim at probably 10 or above. If you go below that, it's going to be quite a slow fermentation. Parts per million oxygen, if you're using wet yeast, it tends to be quite dependent on the strain. So I'd probably start at a level maybe 10 or slightly higher, and then see where you need to go to get the results that you desire. Spontaneous fermentation, yeah, I actually have a presentation on that I gave a few years ago, so I can go over some spontaneous fermentation stuff. Lager is more difficult to brew than ale because it's impossible to hide from off flavors. True or false? I have to say I think that's true. I think there's a lot less to hide behind in a lager. If you're producing big IPAs or brown ales, you've got all the different malt flavors there, especially if you're doing pale lagers, and you've got all the different hops, and it's quite easy to hide behind hops and create a product that's got maybe a fermentation flaw, but isn't quite so noticeable. I think in a lager it really does shine through, and you have to be, very very good at paying attention to detail to do it well. Kettle sour presentation, particular idea of how to measure titratable acidity. Yeah, I've uh, I've got a method for that, and hey, I live in a school, so maybe I can get my wife to lend us the chemistry labs, and we'll do a live demonstration. Powerful. What is the maximum number of generations repitching use that you suggest? We'll skip the business point of view from sales on this question. Pavel, you should use new yeast every time, every time. No, I'm joking, of course. You could probably go up to about 6 generations. Beyond that, you might find it starts to slow down, become a bit sluggish. You might find that you start to get a genetic drift. You can sometimes go beyond that as well, but I think if you want to have a product that's really, really consistent, best to stick at 6. Simon, is it okay to open a bottle of Augustina now? This talk made me thirsty. Yes, absolutely, Simon, but why are you drinking Augustina? Your lagers are so good. Can Krausling produce smoother lager as some extra yeast is added to scrub off some of the polyphenols? Um, I don't necessarily think that it's going to produce a smoother lager just by Krausling it. I mean, polyphenols are quite insoluble anyway, so they should drop to the tank, bottom of the tank given enough time anyway. You might find that the Krausling helps along the process because it probably alters the pH quite nicely, reduces your pH and makes those polyphenols less soluble. So that could potentially be a reason. But I wouldn't like to put money on it personally. Um, maybe is my answer to that one. Cool. There seems to be less questions coming in. I'm gonna again. I'll leave it a few more minutes, and if nothing comes in, then I might go have an Augustina as well. What's your favorite lager? Ooh, it's a tough one. I actually really like the Augustina as well. Um, but I'll say this, and it's proved controversial with some of my colleagues in the past. I actually quite like Pilsner Urquell. I think it's really nice. But certain others within my team will crucify me for saying such a thing. I really, really like it. Right then, there seems to be less questions coming in, so I'm now going to go. But it seems that we have some consensus on what we'd like to talk about next time around. So a few people have said, can we talk about sour beers and spontaneous fermentation? And the answer is yes, absolutely. So I'll get working on that as the next seminar. Um, until then, look after yourselves, find things to do with your self-isolation, and brew lots of beer at home. And feel free to contact me because we brew with you online as well as in person. Cheerio. Bye bye.